Hi class, here is another example of graphing a quadratic equation whose graph is a parabola. Hi class, here is another example of graphing a parabola whose graph comes from a quadratic polynomial. So we're going to find the vertex. So we're graphing y equals negative 2x squared plus 6x minus 5. Find the vertex. X coordinate is negative b over 2a, which is negative 6 over 2 times negative 2, which is negative over negative is positive, so 6 over 4 reduces to 3 over 2. The y coordinate we plug in, we get negative 2 times 3 halves squared plus 6 times 3 halves minus 5. Simplifying, let's see, I get negative 2 times 3 halves squared is 9/4 plus, normally I would, when I did 6 times 3 halves, I would cancel, right? And I'd say 6 divided by 2 is 3, 3 times 3 is 9. But I'm going to leave this as 18 halves because I know that when I cancel the 2's here, I'm going to have a denominator of a 2. And then minus 5. So this is going to equal, so this is negative 2 over 1. You can cancel a 2 here, and that's a 4, believe it or not. It might not look like a 4, but it's a 4. But 2 and 4 cancel only behind the 2 there. So I end up having negative 9 halves plus 18 halves minus 10 halves. Right, because 5 times 2 over 2 is 10 over 2. And then just like every other time, first and second term are opposite signs. Second term is twice as big as the first term. So I end up with positive 9 halves minus 10 halves, which is negative 1 half. So my vertex is x is positive 3 halves, y is negative 1 half. My y-intercept, again we set x equal to 0, and we end up getting 0 plus 0 minus 5, so just negative 5. So that means my y-intercept is the coordinate 0, negative 5. Okay, so let's go ahead and plot these on the xy coordinate system and see if we have x-intercepts. So I've got 0, negative 5 for my y-intercept. So I'll put that like right there. And I had 3 halves common, negative 1 half. Yeah. So I don't know, maybe over a bit, down a little bit. I feel like I graphed. No, that's fine. So there's my vertex. 3 halves common, negative 1 half. And I can see that since this is my vertex, this has to open downwards because I have to hit this point here, right? We can't open upwards, and it always opens upwards or downwards from the vertex. So here my vertex is a maximum. We're going to open downwards, and we're going to hit this point, and then symmetric the other way. And notably here, we don't have any x-intercepts. So no, we don't have x-intercepts. So in this case, you could just leave it like this. Often when we have no x-intercepts, we like to find one more point. And typically it's the point that is at the same height or y level as this point here. So like that point right there has a y value or coordinate of negative 5. And the x coordinate is just however far it is from the x coordinate here to the axis of symmetry, which is x equals 3 halves, it's the same distance from here to there. So since from 0 to 3 halves, the distance is 3 halves, from 3 halves to 3, where we add another 3 halves plus 3 halves is 3. And you could check that if you wanted to, right? You could look at y equals negative 2x squared plus 6x minus 5. If you plug in 3, you're going to get negative, you're going to get negative 2 times 3 squared plus 6 times 3 minus 5. That's going to give you negative 2 times 9 is negative 18 plus 18 minus 5. Those cancel to negative 5. So if you have one of these where you don't have any x-intercepts, you can find another nice point to have on your graph by just taking essentially the mirror image of your y-intercept across the axis of symmetry. So it's 3 halves from here to here. It's another 3 halves from here to here. And then lastly, I would say the maximum value of this function is y -1/2. That is the largest value this graph attains, and it occurs at x equal to 3/2. But I think that's all I have to say about this one, so hopefully that's helpful.